It's not a comet. It's not a satellite. It's not a piece of space junk burning up in the dark. On the night of April 13th, 2029, the point of light you see moving across the sky will be a rock the size of the Empire State Building, and it will be closer to you than the satellites that carry your television signal. Its name is 99942 Apophis. And the part that should hold your attention is this. Nothing this large has ever been tracked, measured, and confirmed to pass this close to Earth in recorded human history. We are not watching an event. We are watching the first one we saw coming. Today we break down everything. What it is, where it came from, why it terrified the people who found it, what happens in 2029, and what comes after. No guessing, just the facts. It begins on June 19, 2004, at Kitt Peak National Observatory in Arizona. Roy Tucker, David Tholen, and Fabrizio Bernardi are running a survey. A faint smear appears across two frames. It is moving. They log it, they report it, and then, as happens constantly in this field, weather closes in, and the object is lost. 2 nights of data is not enough to pin an orbit. The rock disappears back into the sky. It is recovered on December 18, 2004, from Siding Spring Observatory in Australia. Now there is a longer arc of observations. Now the orbit can be computed. And within days, the numbers coming out of the Jet Propulsion Laboratory in Pasadena start doing something that numbers in this field almost never do. The impact probability rises. On December 27, 2004, the calculated chance that this object strikes Earth on April 13, 2029, reaches roughly 2.7%. That is about 1 in 37. It is assigned a rating of 4 on the Torino scale, the 10-point system astronomers use to communicate impact risk to the public. No object before it, and no object since, has ever been rated that high. Understand what a Torino 4 means. It means a close encounter by an object large enough to cause regional devastation, with a probability high enough that it warrants attention from public officials. Not a headline, not a scare, an actual, formal, institutional concern. For a few days at the end of 2004, a small number of astronomers were looking at a real number for a real rock on a real date. And the number was not 0. The object gets a name. Tholen and Tucker choose Apophis, the Greek rendering of Apep, the serpent of the Egyptian underworld, the destroyer who tries to swallow the sun each night. They are also fans of a science fiction show in which the villain carries that name. Both explanations are true. The name sticks because it fits. Then the archive saves everyone. Researchers go back through older survey images and find Apophis sitting there, unrecognized, in data from March 2004. That pre-discovery observation extends the orbital arc backward by months. With a longer arc, the uncertainty region collapses. The 2029 impact probability drops to essentially 0. The rock is not going to hit us in 2029. That was settled 20 years before the flyby. But the trajectory that emerges from the refined math is, in its own way, stranger than the impact scenario. Here is what the mechanism is, and it is simple. Apophis orbits the Sun on a path that crosses Earth's. Earth orbits the Sun. Twice per Apophis year, those paths bring the two objects into the same neighborhood. Most of those encounters are millions of kilometers wide. The 2029 encounter is not. On April 13, 2029, Apophis passes approximately 31,600 kilometers above Earth's surface. That is the number to hold on to. Roughly 31,600 kilometers. Geostationary satellites, the ring of communications and weather platforms that sit fixed above the equator, orbit at 35,786 kilometers. Apophis passes beneath them. It threads inside the highest permanent human infrastructure in space and comes out the other side. For scale, the Moon is 384,000 kilometers away. Apophis will be about 1/12 of that distance. Closer than the Moon by a factor of 12. Closer than the satellites relaying live coverage of its own approach. Now, the size. This is where the estimates matter, because size determines everything about what this object could do. Radar observations from the Goldstone antenna in California and the Arecibo dish in Puerto Rico, combined with infrared measurements from the Herschel Space Observatory in 2013, converge on a diameter of roughly 340 to 375 meters along its longest axis. Herschel's figure was 375 meters, plus or minus about 10. It is not a sphere. Radar imaging shows an elongated, bilobed body, two rounded masses joined at a neck, the shape astronomers informally call a peanut. It is a common shape among small asteroids, and it usually means the object is not a single solid slab, but a loosely bound structure, or two bodies that merged gently in the distant past. It does not spin cleanly, either. Apophis tumbles. It rotates on more than one axis at once, with periods of roughly 30.6 hours and 27.4 hours superimposed. There is no fixed north pole. From the surface, if you could stand on it, the sun would rise in a different place every time. Its composition is classified as SQ-type, stony, silicate-rich, chemically similar to the ordinary chondrite meteorites that make up the majority of falls recovered on Earth. Not iron, not ice. Rock. Mass estimates cluster around 27 billion kilograms, though that figure carries real uncertainty because we do not yet know the interior density with confidence. Mark that as uncertain. It is one of the specific things the 2029 missions are being sent to measure. So what would 27 billion kilograms of rock arriving at cosmic velocity actually do? The calculated impact energy sits near 1,100 to 1,200 megatons of TNT equivalent. For comparison, the largest nuclear device ever detonated, the Soviet Tsar Bomba, in 1961, yielded about 50 megatons. Apophis carries the energy of more than 20 of them, released in a single instant. This is not an extinction event. That distinction belongs to objects like the Chicxulub impactor of 66 million years ago, which was around 10 kilometers across, roughly 30 times the diameter of Apophis, and thousands of times its mass. Apophis is in a different class entirely. It is what planetary defense specialists call a regional devastator. A land impact would excavate a crater several kilometers wide and flatten structures across an area comparable to a small country. An ocean impact would generate tsunamis capable of reaching coastlines hundreds of kilometers away. Millions of lives sit inside the plausible outcome range, depending entirely on where the point of contact falls. Set that against the two impacts in modern memory. The Tunguska event of June 1908 flattened over 2,000 square kilometers of Siberian forest, an estimated 80 million trees, and the object responsible is thought to have been somewhere near 50 to 60 meters across. It never even reached the ground. It detonated in the air. On February 15, 2013, a roughly 20-meter object entered the atmosphere over Chelyabinsk, Russia, at around 19 kilometers per second. It exploded at altitude with an energy near 500 kilotons. The shockwave shattered windows across 6 cities and injured approximately 1,500 people, almost all from flying glass. Nobody saw it coming. It arrived from the direction of the sun, in our blind spot. 20 meters caused that. Apophis is close to 370, but it is not going to hit us in 2029. That is not a hope, it is a measurement. And in 2021, that measurement was extended by a century. In March 2021, Apophis made a distant pass, around 17 million kilometers, and astronomers used it. The Goldstone antenna transmitted radar pulses at the asteroid, and the Green Bank telescope in West Virginia received the echoes. The technique measures distance and velocity with extraordinary precision, far beyond what optical telescopes can achieve. The refined orbit ruled out any impact risk for at least the next 100 years. Apophis was removed from the Sentry Risk Table, the automated list of objects with non-zero impact probability maintained by JPL's Center for Near-Earth Object Studies. After 17 years on the list, much of that time as its most prominent entry, it came off. No guessing, just the facts. The 2029 approach is a flyby. The mathematics is closed. But there is a concept buried in that 17-year history that deserves its own explanation, because it is the reason the 2029 pass was studied so obsessively, even after the impact was ruled out. The concept is a gravitational keyhole. Here is the mechanism, and it is simple. When Apophis passes Earth in 2029, our gravity will bend its path. How much it bends depends on exactly where it passes. A trajectory a few hundred kilometers to one side gets deflected slightly differently than a trajectory a few hundred kilometers to the other. Within the wide corridor Apophis will fly through, there exist narrow regions, some only a few hundred meters across, where the deflection would be precisely tuned to send the asteroid back into a collision course on a later return. Those regions are keyholes. Pass through one, and the 2029 flyby becomes the setup for a 2036 or 2068 impact. This is the strange arithmetic of orbital mechanics. A difference of a few hundred meters in 2029 becomes the difference between a near miss and a strike 4 decades later. The keyhole for 2036 was measured at roughly 600 meters wide. Apophis will miss it by a wide margin. The 2068 possibility, which lingered longest in the literature, was eliminated by that same 2021 radar campaign. Every keyhole has been cleared. What remains is the flyby itself, and the flyby is going to be visible. At closest approach, Apophis is expected to reach an apparent magnitude near 3.1. In the astronomical brightness scale, lower numbers mean brighter, and magnitude 6 is roughly the limit of unaided human vision under dark skies. Magnitude 3.1 is comfortably above that threshold. Be precise about what that means, because the popular framing overstates it. Apophis will not outshine the stars in the sense of dominating the sky. It will not rival Venus, or Sirius, or Jupiter. At magnitude 3.1, it will look like one of the middling stars of the Big Dipper, an ordinary point of light, easily visible, entirely unremarkable to the eye. What makes it extraordinary is that it moves. Stars are fixed, satellites are faint and small. Apophis will cross the sky at a rate that is obvious in real time, a star-like point, sliding steadily against the constellations, covering large stretches of sky over the course of a few hours. You will not need a telescope. You will not need binoculars. You will need a clear sky and the knowledge of where to look. The viewing region is Europe, Africa, and Western Asia. Roughly 2 billion people will be under the correct part of the sky at the correct time. It will be the first time in recorded history that a body of this size has been visible to the naked eye during a close approach to Earth. Statistically, an object of this size passing this close is estimated to occur roughly once every 7,500 years. Every human being alive on April 13, 2029, will be present for something the species has almost certainly never observed, and may not observe again for millennia. And it will not just pass, it will be changed by us. Apophis currently belongs to the Aten class of asteroids, objects whose orbits lie mostly inside Earth's, with a period shorter than 1 year. Its orbital period is about 324 days. Earth's gravity will alter that. The encounter will stretch its orbit outward, converting Apophis into an Apollo-class asteroid, with an orbital path lying mostly outside Earth's and a period extended to roughly 424 days. 100 additional days added to its year in the space of a few hours by a single gravitational handshake. The object will also be physically deformed. This is one of the most interesting predictions in the field, and it comes from work by Richard Binzel at MIT and others who have modeled the encounter in detail. Here is the mechanism. Gravity does not pull equally on a large object. The side of Apophis facing Earth will be pulled slightly harder than the far side. That differential is a tidal force, the same effect that raises ocean tides on Earth and cracked the comet Shoemaker-Levy 9 into fragments before it struck Jupiter in 1994. Apophis is not a solid monolith. Objects of its size and class are typically rubble piles, assemblages of boulders, gravel, and dust, held together by weak self-gravity and friction. A structure like that responds to stress, the way a bag of sand does, not the way a boulder does. The models predict surface effects, landslides on its slopes, seismic shaking that lifts dust off the surface, boulders rolling and resettling, possibly a measurable change in its spin state. Fresh, unweathered material may be exposed for the first time in millions of years. This is why the missions matter, because we will be able to watch a planetary body be physically reshaped by tidal forces, at close range, with instruments, and we will have a before and after record. NASA's contribution is a spacecraft that already exists. OSIRIS-REx spent years at Asteroid Bennu, collected a sample, and delivered that sample to Earth on September 24, 2023, when the return capsule landed in the Utah desert. The spacecraft itself did not land. It released the capsule and kept flying. It was renamed OSIRIS-APEX, the apex standing for Apophis Explorer, and redirected. Its trajectory brings it to Apophis shortly after the April 2029 flyby, where it is planned to enter orbit and study the asteroid for approximately 18 months. One planned maneuver stands out. The spacecraft is designed to descend to within a few meters of the surface, and fire its thrusters directly at the regolith, blowing away the surface layer to expose what lies beneath. No landing, no drilling. Just an engine burn, used as an excavation tool. The European Space Agency's contribution is Ramses, the Rapid Apophis mission for space safety. The concept is to launch in 2028 and arrive at Apophis before the flyby, so that the asteroid can be measured in detail on approach, observed continuously through the encounter, and measured again afterward. That before and after coverage is the entire scientific point. OSIRIS-APEX arrives after. Ramses would be there for the whole thing. Mission funding and schedule status has moved through ESA's decision-making process and should be treated as subject to change. Mark that as uncertain. The scientific case for it is not in dispute. What comes out of these missions is not just knowledge about one rock. It is calibration data for the entire discipline of planetary defense. Because here is the problem the field actually faces. To deflect an asteroid, you need to know its mass, its internal structure, and how it responds to force. Push a solid iron body, and it moves as a unit. Push a loosely bound rubble pile, and the energy dissipates into the gaps between boulders. Or it fragments, or it absorbs the impulse and barely shifts. We have done this once. On September 26, 2022, NASA's DART spacecraft deliberately struck Dimorphos, the small moon of asteroid Didymos, at roughly 6 kilometers per second. It worked. Dimorphos's orbital period around its parent was shortened by about 32 minutes, far exceeding the mission's minimum success threshold of 73 seconds. That was one test, on one object, of one composition, at one geometry. It proved the principle. It did not produce a general theory. Every asteroid is a different structure, and the response to a kinetic impact depends on details we cannot measure from Earth. Apophis, studied up close while being physically stressed by a planetary gravity field, is a natural experiment we could never ethically or affordably run ourselves. Earth applies the force. We measure the response. Nobody had to build anything to deliver the impulse. There is one more measurement worth explaining, because it is the reason long-term predictions for objects like this remain hard even after the orbit is nailed down. It is called the Yarkovsky effect. Here is the mechanism, and it is simple. An asteroid absorbs sunlight on its day side and heats up. Because it rotates, that heat is not radiated straight back toward the sun. It is carried around and radiated from the afternoon side, at an angle. Radiated heat carries momentum. The result is a tiny, continuous thrust. The force is minute. On Apophis, it amounts to a drift of roughly 170 meters per year away from the purely gravitational prediction. Over a single orbit, negligible. Over a century, it is tens of kilometers. Over the timescales that matter for keyhole calculations, it is the difference between a prediction and a guess. That drift was detected and measured in 2020 and 2021 by researchers analyzing years of tracking data. It is now built into the models. It is a large part of why the 100-year all clear could be issued with confidence. So let us assemble the worst case honestly, because that is the exercise the numbers were originally run for, and because the same numbers apply to objects we have not found yet. If a body of Apophis's dimensions struck a continental landmass, it would arrive at somewhere between 12 and 20 kilometers per second. It would not slow appreciably in the atmosphere. An object 370 meters across carries far too much momentum for air resistance to matter. Contact releases roughly 1,150 megatons in a fraction of a second. The crater would be several kilometers wide and hundreds of meters deep. Rock at the impact point is vaporized outright. A shock wave propagates outward through the ground and the air simultaneously. Thermal radiation from the fireball ignites combustible material across a radius of tens of kilometers. The air blast that follows levels structures well beyond the burn zone. Ejecta, pulverized rock thrown clear of the crater, rains back down across a far wider area, some of it re-entering the atmosphere and heating the sky. Seismic energy, comparable to a major earthquake, radiates from the site. Dust and vapor loft into the upper atmosphere, and depending on the target composition, that could measurably affect regional climate for months. An ocean impact substitutes one catastrophe for another. Deep water impacts generate waves that spread across an entire basin. Coastal populations across multiple countries would face inundation with warning times measured in hours. That is the scenario the Torino 4 rating referred to in December 2004. That is what 1 in 37 meant. And for a few days, before the archival images were found and the orbit was refined. That was the live calculation. It is worth sitting with that. The margin between the world we live in and that scenario was not engineering or diplomacy or defense. It was a set of photographic plates taken in March 2004 by people who did not know what they had recorded, sitting in an archive until someone went looking. Which brings us to the part that is genuinely unresolved, and the reason none of this is merely a story about one rock. Surveys have cataloged the overwhelming majority of near-Earth asteroids larger than 1 kilometer, the true civilization-scale threats. That work is essentially complete, and the finding is reassuring. None of the known ones are on a collision course this century. The population Apophis belongs to is a different matter. Objects in the 140-meter to 1-kilometer range, large enough to devastate a region, small enough to be faint, number in the tens of thousands, and a substantial fraction of them have never been detected. Not tracked poorly, not detected at all, and there is a permanent blind spot. Objects approaching from the direction of the sun are lost in glare and cannot be seen by ground-based optical telescopes. Chelyabinsk came from exactly that direction. It was invisible until it was already burning. That gap is what NEO Surveyor is designed to close, an infrared space telescope built specifically to detect dark, faint, near-Earth objects that reflect too little visible light to be found from the ground, including those approaching from sunward directions. Infrared detects the heat an asteroid emits rather than the light it reflects, which makes dark objects visible instead of invisible. So the honest summary is this: Apophis in 2029 is not a threat, it is a rehearsal. It is the one time we get to study an object of this exact class, at this exact range, with warning, with instruments already built and en route, and with no consequences riding on the outcome. We got 2 decades of notice on this one. The next object may be found with 2 decades of notice, or 2 years, or 2 days. That variable is not determined by the asteroid. It is determined entirely by how many telescopes are looking, how much sky they cover, and whether the funding for that work survives from one budget cycle to the next. On the night of April 13, 2029, if you are anywhere in Europe, Africa, or Western Asia, and the sky is clear, look up. You will see a point of light that looks like an ordinary star. It will be moving, and it will be a piece of the early solar system, 4.5 billion years old, passing beneath our satellites, at a distance we can name to the kilometer, on a date we have known for 25 years. That is the achievement, not the rock, the fact that we know. The single takeaway is this: Apophis will not hit Earth in 2029, or at any point in the following century. That is measured, not hoped. What it will do is pass closer than our own communications satellites, visible to the unaided eye, while 2 spacecraft watch a planetary body be reshaped by Earth's gravity in real time. Subscribe. We track this as it develops. Every orbital refinement, every mission milestone, every image that comes back from Osiris Apex. And if you want to know what happens when we do not get 25 years of warning, watch the next one, the asteroid that hit us in 2013 with 0 seconds of notice, and what it revealed about the blind spot we still have not closed. No guessing, just the facts.